until I free up all the available 32G on my memory card for my camcorder, handy cam. I have about 7G. That works out at about an hour and 50, a bit under 2 hours filming. And I now have about 21 minutes, so I'll try to, I don't want to have to download and then film again, just download once. So I'll try to do this in about 20 minutes. Alright, now we're trying to prove the second condition, and that was if you concatenate V and Y, the size of that, Vy, has to be positive, it can't be 0. And so if both of these, the V and Y, if they're both the empty string epsilon, well then if you substitute if you throw away the larger subtree and you substitute it, replace it by the smaller subtree, then the resulting parse tree, it would have fewer nodes than tau. Now remember tau, but we set up tau, we chose tau to be the parse tree with the least number of nodes. Okay, so you got yourself a contradiction, and therefore you cannot have both V and Y being the empty string. Okay, so you're using a proof by contradiction, right? So just thinking by contradiction. And that's why we set up tau in that way in the first place, to get this contradiction, so that we can prove that V and Y cannot both be the empty string epsilon. Okay, all right. Now how about condition 3? Now, just a reminder, what was condition 3 in the pumping lemma? It was this: the size of if you concatenate Vxy, so the size of it, the number of elements in the string, in other words, it's going to be less or equal to P. P is the pumping lemma, and we defined, well not defined, we specified, we made P in this previous session. We defined it to be little b raised to power mod V plus 1. Okay? Alright. And we have to show, on the basis of that P, little b raised to mod V plus 1, we have to show that's greater or equal to this, effectively. Okay? Now in the parse tree for your string S, okay, that you choose that particular path that had we said, say, 2 occurrences of R. That was the repeat variable. So for the upper occurrence of R, it will generate a parse tree. Its parse tree will generate this string of, or substring of terminals Vxy. Okay, and let's see. And we chose that repeated so that it lay in the bottom V mod V plus 1 variables. Okay, we chose that, and this is what, in this proof we're doing now, you'll see why. Okay, and so now let's choose. So we choose the longest path in the path tree. Okay. So where in the parse tree, the subtree that R generates, where R generates this, Vxy. Okay, and so let me get rid of this. So let's see. So its height, will be at most this, right? So you're choosing your R, the repeat. It's to lie, and that repeated variable generates this substring Vxy, and the height of that path from R is this much. Okay. Now, Now, from the earlier session, we showed that a tree of that height, this height here, it can the maximum length string it can generate would be this. Okay, it would be that. So that will be P. Now why is that? That doesn't make sense, because we defined P to be B of V plus 1. Now I'm getting a little confused. Sorry, I thought I'd clicked, but I haven't fully. Anyway, Sipser ends here, and then I put this in it for a bit of clarification. Now that I'm in the immediacy of the moment, I realise I haven't fully clicked, so probably I'll explain it to you again next session. Now I put this in for clarification. So let's see. Now, so the length of this substring vxy would need to be less than this, less or equal to this, and therefore, but that equals P. You define that to be P, and therefore the length of this string has to be less or equal to P. I just put that in. That comes from this. Now, where this comes from, why it's 2, I need to think about it more. This is new to me. I thought I followed it by writing it up on the board, but I have a question mark. All right. Okay. Now the next stuff, general comment. It's the use of the pumping lemma, in this case for context-free language, very similar to what we did in using the pumping lemma for regular languages. So typically you'll choose a particular string that belongs to the language, and you'll show that it cannot be pumped. So you'll assume, let's now here's a particular example, 2.36, the first of our 3. Here's the language B that you're given, and you're asked to show that B is not context-free. In other words, you'll apply the pumping lemma to this language. So let's choose a particular string. So we'll choose it to be. Doing this kind of thing is just what we did earlier, the 5 examples we did with regular languages. So we'll choose a particular string, A to the P, B to the P, C to the P, where P is the pumping length, and we will prove that when this is pumped, that it does not belong to this language. Right? So I will end there. I need to study this a bit more so that it clicks, and I suggest you do the same, because it's an important proof. Ciao.